Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome to the online lecture of nonlinear control systems. Today this is our fourth lecture of the course, and we will start with the where we left off in lecture number 3. We were discussing the local existence and uniqueness theorem for the solution of nonlinear ordinary differential equation. So this is what we had: the differential equation x dot equal f of x, f of t comma x, which f is the function of time and it's also the function of x, which x itself is the function of time, and there is some initial condition x naught. Then if f of t comma x is piecewise continuous in time and there exists finite constant capital T greater than t naught and gamma greater than 0 and Lipschitz constant less than infinity, such that f is Lipschitz continuous with Lipschitz constant L, then Lipschitz continuous within the neighborhood gamma of x naught and for time interval t naught to capital T, then we can claim that there exists some other interval t naught to t naught plus delta t in which the solution exists and is unique. So this is the theorem that we discussed last time. Now we will look at the proof of this theorem. So we already know that this delta, the interval of the existence of solution, it is not yet specified by the theorem. So we just know that there is some delta. So we can select any delta and try to prove the theorem, and then we will see how things work out. First of all, we know that there is a notation for continuous functions. We have seen this in the previous lectures, that if phi of t is a continuous function from t naught to t naught plus delta t, then it can be represented by c sub n c sub n from interval t naught to t naught plus delta t. So this is just a notation for continuous functions which are defined on this interval. So we already know that the solution of differential equation is going to be a continuous function, so that is why we are defining a new function p, which is a function of continuous functions to other continuous functions. So this is a function which takes in a continuous function and generates another continuous function, and it is defined like this: p is a function and a function of x and t. Basically it's a function of phi of t and you can say t itself with some initial condition x naught. So the way we have defined this p function is exactly the same way that we defined the solution of a differential equation. Okay, so this p is a function, it's a function of phi of t, and phi of t is a continuous function. So p takes in a continuous function and generates this whole thing. This whole thing is also a continuous function because it's like a integral of a piecewise continuous function plus some initial condition, and the integral is also definite, so we have no problem here. If x of t is a fixed point of t, so now we are talking about contractions. So we have defined a function. If this function is some sort of a contraction, we have already discussed the definition of a contraction. So if x of t is a fixed point of p, i.e. that x of t, p of x of t is equal to x of t, then x of t is the solution of ordinary differential equation. We can see that from the definition of p. So if x of t is equal to this whole thing with phi of t replaced by x of t, then definitely x of t would be the same thing as the solution of the differential equation that we have discussed in the previous lectures. So this is the purpose of defining p in this way. The purpose of defining p in this way is that if we somehow prove that P is a contraction, then the fixed point of P would be the solution of the ordinary differential equation. And if we prove that P is a contraction, then by contraction mapping theorem we would know that P must have a fixed point. So if P must have a fixed point, then that fixed point is a solution of differential equation. That would prove that the solution of differential equation would exist and would be unique. So that is all we are trying to prove. We are trying to prove that the solution of a differential equation, the differential equation that we are discussing, does exist and it is unique. We are trying to prove that, and we are going to prove that using the contraction function here, by proving that that P is a contraction. So when is P a contraction? What are the conditions under which the P is a contraction? You already, if you recall the definition of a contraction, that is very similar to the definition of Lipschitz continuity, but we'll just revise it here. So I have repeated the definition of P on this slide. Let x, y be some continuous functions. Then since f of t comma x is Lipschitz continuous with respect to x, therefore P of x minus P of y, which is basically integral of f plus some constant, so it will also satisfy the Lipschitz property. So P of x minus P of y would be less than equal to some constant. This might be the Lipschitz constant times x minus y, the norm of x minus y. Note that we have used the infinity norm here because continuous functions over the set of real numbers with infinity norms, this is a complete space. So we don't have to worry about, you know, Cauchy and converging sequence problem. Every Cauchy sequence will be converging in this space, and we will not have to worry about whether the fixed point of P lies within this space or not. Okay, now we need to show that there exists this C. All we need to show is that this Lipschitz constant is less than 1. If this is less than 1, then this becomes the constant of the definition of a contraction, and then P will be proven to be a contraction. All we have to prove is that this C is less than 1 under some conditions. For that, we take the supremum of P of x minus P of y over all the time interval from t0 to t0 plus delta t, over which these functions are defined. And similarly, we take supremum on the right hand side as well, because x and y are also function of time. So if this supremum is less than equal to this supremum times C, where C is shown to be less than 1, then we will be done. We will have proven that the solution of the differential equation exists and is unique. So first of all, what we do is we fix the t. By fixing the t, what we do is that we show the inequality for one arbitrary t, and showing it for a single arbitrary t will mean that for any particular value of t it will hold. So if it holds for any arbitrary value of t, then we can sum up and take supremum. I will show you how we prove this once we fix the value of t. So if you fix the value of t, P of x of t becomes simple P of x, P of y, the t is now fixed, and this is the integral from t naught. So if you subtract P of x minus P of y, x naught will cancel out because it is a constant, same in both P of x and P of y. The only thing that will remain is the integral of f of x minus f of y. Note that with fixed t, px and py are just n cross 1 vectors. They are not functions of time. So P of x minus P of y, if you take infinity norm on both sides of this equation, then this is the situation. And if you use triangular inequality states that the norm of a sum is less than or equal to sum of norms. So you take sum of norms, then that would be less than greater than, sum of norms will be greater than the norm of sum. So applying triangular inequality, we have reached to this conclusion, and now using the Lipschitz continuity of this f, we can replace fx minus fy with L into x minus y, because Lipschitz continuity is given in the theorem. So we can use the given conditions to try to prove the claim. So using Lipschitz continuity, we arrive at this situation where we have integral from t0 to t L times x minus y norm, and this is greater than or equal to px minus py. Next, what we do is that we perform this integral, because this here we have fixed t, so these are not functions of time, so it will be simple that the integral of this whole thing will be t minus t naught times x minus y, and this L does not disappear, this L is still here. I have missed it in writing, so I will just put it back. Okay, so next is that p of x minus p of y is less than equal to L times this t minus t naught, and so we have arrived here, and therefore if we take the supremum, now we have used this, we have arrived at this situation using by fixing the value of t, but by fixing the value of t arbitrarily. So this is true for any arbitrary value of t. What about the interval from t0 to t0 plus delta? So for that, we take the supremum over all possible values of t within this interval on both sides, and that will not change the inequality. So if you see that on this side the supremum remains supremum, but on this side, if you see, t is not appearing here, t is appearing here. So in this term, if you apply the supremum, then t minus t naught will have the maximum value. In this case, the maximum does exist because the set is closed, less than or equal to on both sides. So the maximum value of this difference would be when t is t naught plus delta, because when t is t naught, then t naught minus t naught is 0. When you increase t naught, you can increase it to the extent where it is t naught plus delta, that's the maximum possible extent. So the maximum of this t minus t naught is delta. So this is the supremum or maximum, so L delta. So we have arrived at this situation, and this is by over all the range of t. And now if you look closely at this situation, p of x minus p of y, this whole norm is less than or equal to L delta times the norm of x minus y. Now this is if L delta, hence the sufficient condition for p to be a contraction is L times delta to be less than 1, or the delta, which is the interval of the existence of solution, to be less than reciprocal of the Lipschitz constant of the f of x function, for which the Lipschitz continuity is given in the theorem. So given that we have x dot equal f of x, where f of x is Lipschitz continuous with Lipschitz constant L, the solution will exist for the time interval t0 to t0 plus delta, where delta would be less than 1 over L. So that is that does not only prove the theorem, but we prove the existence of the solution by proving that p is a contraction under certain condition. But this given condition for p to be a contraction also tells us that for how long the solution might exist. So the interval of existence of solution has been emerged from the proof of the theorem as a bonus. So this type of proof is called constructive proof. So this is a constructive proof because it does not only prove the claim, but it also gives us additional information about the claim that we did not know. Okay, so there is a corollary for this theorem. Suppose that f of t comma x is piecewise continuous in time, and there exists gamma greater than 0, t greater than t naught, and L less than infinity, such that the Jacobian of f is less than L. The magnitude of the Jacobian of L is less f. The magnitude of the Jacobian of f is less than L for all the gamma neighborhood of the initial condition and this interval. Then there exists delta greater than 0 such that this differential equation will have exactly one solution. So this is again existence and uniqueness, but in terms of the bound on the Jacobian of the f function, or the bound on the slope of f function. This is very similar to what we saw in Lipschitz continuity, that Lipschitz continuity can also be defined in terms of the bound on the slope. Similarly, we can define the existence and uniqueness of the solution of the differential equation in terms of the bound on the slope. Okay, so then there is global existence and uniqueness. Global existence and uniqueness is different in two ways. First of all, the f is supposed to be piecewise continuous for all t from t naught to infinity, and secondly, it's supposed to be Lipschitz continuous for not in just neighborhood of the x naught, but it is supposed to be Lipschitz continuous for all x y in Rn. So these are the two differences. One difference is that the Lipschitz continuity is the piecewise continuity is of f is for t naught to infinity, and similarly the Lipschitz continuity is for all the space, all the points in the space, not just in the neighborhood of x naught, not just in the neighborhood of the initial condition. And then this is also t naught to capital T. So here capital T belongs with t naught to infinity. So this interval is also not finite. It does not have to be a small interval. I mean, it can be arbitrarily large interval. Then for all t belonging to t naught to infinity, this differential equation will have exactly one solution, and this is basically the global existence and uniqueness. So local existence and uniqueness requires f to be piecewise continuous and Lipschitz continuous over a small neighborhood of the initial condition and for a finite interval of time. But global, and the claim of the local theorem is also the existence and uniqueness for local for some interval of time. But global requires f to be piecewise continuous and Lipschitz continuous globally, and its claim is also that the solution will exist for all possible lengths of time interval and for all initial conditions, not just one given initial condition. So this is the difference between local and global existence and uniqueness theorem. We will not go into the proof of this theorem because seeing the proof of local existence and uniqueness theorem should be enough education as far as this course is concerned. You are most welcome to explore the literature and find out the proof of global existence and uniqueness theorem that you can learn on your own. So let's look at some examples of existence and uniqueness theorem. First of all, look at this system x dot equal ax plus bu. This is a linear system that is known to the students of nonlinear systems in general, with initial condition x of t naught is equal to x naught. There, if you apply, try to apply the existence and uniqueness theorem, you see that f of x here is a times x plus b times u, and you can already see that f is Lipschitz continuous with the Lipschitz constant induced norm of A, and so since this Lipschitz constant does not depend upon x or y, so this is globally Lipschitz. So f here is globally Lipschitz. It is not Lipschitz just in the neighborhood of any x naught. It is Lipschitz because this A matrix have induced norm independent of this value of x naught. So this hence there is global existence and uniqueness for all piecewise continuous input u. So as long as u is piecewise, why do we need u to be piecewise continuous? Because we know that we need to integrate this u of t. So if it is not integrable, then we will have a problem. So and also when we discussed the definition of the solution of differential equation in lecture 3, we established that the solution has to be at least piecewise continuous. It does not have to be differentiable, but it has to be at least as smooth as piecewise continuous. Okay, for time varying A matrix, the solution still exists and is unique globally if each element of A is continuous. So in that case, the induced norm of A will be finite, but it will change with time. So linear systems, time varying or time invariant, both have global existence and uniqueness of the solution of the differential equation. This is no surprise because in linear systems theory we already see the solution formula for such equations. Next is the example of a nonlinear scalar system, x dot equal 1 plus x square. X square is a nonlinear term. So let's suppose initial condition is x of 0 equals 0. Then we know from our knowledge of calculus that the solution of this x dot equal 1 plus x square is x of t equal tangent t, and with this will have a finite escape time because at time pi by 2 their tangent t will go to infinity and there will be no global existence and uniqueness. But here we want to do this, we want to arrive at this conclusion not by the knowledge of our calculus, but we want to arrive at this conclusion using the existence and uniqueness theorem. So let us look at this from that point of view. So as far as the existence and uniqueness theorem is concerned, we have f of x equal 1 plus x square. That means that partial f by partial x is 2x, which is basically the Jacobian, and it is 1 cross 1 in this case because it's a scalar system. So if you take the magnitude of this slope or magnitude of this Jacobian, then this magnitude is not limited. It can be less than or equal to, let's say, 4 when x is between -2 and 2. So if x is in a local neighborhood of this initial condition, then you can have a bound on the Jacobian. If you don't have, if you don't restrict x, then there will be no restriction on this bound. So there will be delta. In this case, the solution will exist and will be unique on some interval delta. We already know that delta will be less than 1 by 4 from the proof of the local existence and uniqueness theorem. We know that delta will be less than 1 over L. Here L is 4 for this neighborhood. So this is gamma, ball of radius gamma. So here radius is 2. So gamma is 2 here. So you can see here that locally the solution will exist, but globally if you don't restrict this x, then there will be no restriction on this. So global existence and uniqueness is not guaranteed here because this slope is the bound on the slope is dependent upon the bound on x, whereas in the previous example the induced norm of A was independent of x. So here local existence is proven by local existence and uniqueness theorem. And next is the example of this another nonlinear system, x dot equal x raised to the power 2 by 3, which can also be written as sine of x and into cube root of x square. And we claim that this is not x raised to the power 2 by 3 is not Lipschitz continuous at x not equal to 0. So this might be Lipschitz continuous everywhere else, but it is not Lipschitz continuous at this point. And if it is not Lipschitz continuous at this point, then zero initial, so the solution of this differential equation will not exist and will not be unique if the initial condition is 0. Okay, proof. Suppose that there exists gamma greater than 0 and L less than infinity such that this function is indeed Lipschitz continuous. So we are trying to prove by contradiction. So our claim is that this is not Lipschitz, but we are trying to prove this claim by assuming that it is Lipschitz, and we run into contradiction, and that will be the proof. So we set y equal to 0, which is we can do that because technically we can select any xy from the neighborhood gamma of 0. So 0 is within the neighborhood, actually it's right on the 0, so it's no matter how small this neighborhood is, this y will be in this neighborhood, so we can set y equals 0. Setting y equal to 0, this simplifies this inequality, and if we take x on the other side, we will have this L greater than equal to 1 over x raised to the power 1 by 3, and this is a problem because the inequality cannot hold for any value of L, because 1 over x raised power 1 by 3 goes to infinity as x goes to 0, because 0 raised to the power 1 by 3 is 0 and 1 over 0 is infinity. So that is why we cannot have any Lipschitz constant that would guarantee the Lipschitz continuity of this function around 0. So that was another example where according to the local existence and uniqueness theorem, the solution will not exist around with the initial condition x not equal to 0, because at the point 0 this function is not Lipschitz continuous. Okay, so this is not Lipschitz continuous at x not equal to 0. So finally, before we finish the lecture, we will just discuss one Gronwall-Bellman inequality, and we will discuss this inequality briefly in this lecture, and then we'll continue this discussion into the next lecture. Suppose that we have a constant lambda and we have a continuous function mu from the interval a b to real numbers, and this continuous function is non-negative, and under these conditions, if we have another continuous function y that satisfies this inequality, then y will also satisfy this inequality. So what is the difference between the two inequalities? That the second inequality basically is explicit, it does not involve y, and whereas the first inequality involves y. So in detail, if you look at this, y of t is less than equal to some constant times integral of the product of y and u, and there is a function which has an upper bound, but the upper bound is depend upon the function itself, so it's very difficult to use this upper bound in any way. But the Gronwall-Bellman, they proved that if this is true, then this implies this. So if you rewrite this in terms of this, then this is lambda times exponent of the integral of mu of tau, and now you can find the upper bound on y of t in terms of the integral of mu of t times lambda, which is more doable. but this is not enough. I mean, this may not be satisfactory. Why are we discussing this anyway in the nonlinear systems class? So this is a nonlinear control systems lecture. Why are we discussing it here? So we have to see the relevance of Bellman, Gronwall-Bellman inequality in terms of, we have just seen the solution of differential equations. So y of t equal lambda plus integral of mu times y. This is basically the solution of this differential equation, x dot y dot equal mu times y, with initial condition y of a equals lambda. So this basically is similar to the solution of a differential equation. That is why we are so much interested in it. And if you use the inequality to this solution, then you can write the solution in the form of lambda times exponent of integral of a to t mu of t. So for those who know about linear systems, consider this x dot equal ax, and the solution would be something like this, but you can also write the solution into x naught times e to the power integral of ax, or x naught times e to the power at if a is constant. So we already know this. We have used sort of in linear systems theory, but it is good to know the original Gronwall-Bellman inequality that is relevant to the nonlinear control system students. This basically has its application in solving the differential equation. So that's the end of lecture. Let me just briefly revise and go through what we have discussed today. So this was lecture 4. So we started by recalling the local existence and uniqueness theorem, which requires f of x t comma x to be piecewise continuous in time and Lipschitz continuous in x, and it claims that there is some interval in which the solution will exist. We looked at the proof of this theorem. For proving the theorem, we defined a function, and we said that if this function is a contraction, then the solution will exist. And we proved the function to be a contraction by using the Lipschitz property of f of x, and that for p of x, the Lipschitz constant, if it is less than 1, then it is a contraction, and this has to be true for all the t in the interval from t naught to t naught plus delta. But in order to prove this for all the t in the interval, we first fix the time, and by fixing the time, it allowed us to simplify and find some inequalities which are helpful for us. And once we are at a comfortable stage, we again unfix the t. By unfixing the t means that we come back to that interval where we started from, and we apply this expression inequality that we have derived for an arbitrary value of t. We plug it in here and find the supremum on the right hand side, and that gives us the conditions under which p would be a contraction. And so under these conditions, p would be a contraction, and so that will prove that under these conditions the solution will exist and will be unique. And what are the condition? The condition is that the delta has to be less than 1 over Lipschitz constant for the f of t comma x function. So the corollary is that if the magnitude of the Jacobian is less than some Lipschitz constant, then you will still have exactly one solution on t naught to t naught plus delta. Again, here delta will be less than 1 over L. And then global existence and uniqueness is different in two ways. First of all, it does not require Lipschitz continuity in the neighborhood of the initial condition. It requires Lipschitz continuity over all the space. Secondly, it requires it for any arbitrarily long interval of time rather than requiring it for a finite interval of time. And the claim is also global. So claim of existence and uniqueness of the solution does not depend upon a particular initial condition. Initial condition can be anything, and also the solution will exist for arbitrarily long intervals of time. Okay, so then we looked at three examples. First of all, we looked at the linear systems, how existence and uniqueness theorem tells us that the solution for linear systems will exist and will be unique globally. Then we looked at nonlinear system, for which the existence and uniqueness is local, because here this bound depends upon the bound on x. If there is no bound on x, there is no bound here, and there will be no existence uniqueness. I mean, you cannot have global Lipschitz continuity, so that means you cannot have global existence and uniqueness. That we can know from our knowledge of calculus, but we want to know it from the theorem as well. Then we looked at an example where there is no Lipschitz continuity at the point x not equals 0. So around this point their solution cannot exist, and we have proven that this function is indeed not Lipschitz continuous around this point 0 by contradiction. And then we discussed Gronwall-Bellman inequality, which turns an implicit bound into an explicit bound. And why is this important? Why is this relevant? The importance is that it turns implicit bound into explicit bound, but the relevance is that it is used in solving differential equations. So that is it for this lecture, and let me know if you have any questions. Thank you for listening.